Now let's practice conservation of energy on a system that experiences both heat transfer and work. One category of problems like this that we'll encounter often in this class are called piston problems. So a piston consists of a cylinder that contains some fluid. Now fluid is not synonymous with liquid. A fluid can be a liquid, but it could also be a gas. Basically just some substance that has no fixed structure where the internal parts of it can flow past the other parts relatively unimpeded. So the cylinder contains some gas in this case, and the piston out here will push in when there's an external force applied. So it pushes in and compresses the gas inside. And in this particular scenario, the piston is sealed so that none of that gas can escape out the sides or anything like that. So we'll release the force and let the piston push back out from the gas pressure, presumably. Now what if we had a system like this, where a piston compressed a gas, and simultaneously we allowed there to be heat transfer across the piston boundary, like so. There's an external force, and then those red wavy lines indicate heat transfer. And I've drawn the arrows so that the arrows actually indicate the direction of heat transfer. Heat is leaving the gas, exiting the system, going out into the environment. Well, if we know that the piston has traveled a distance of 45 centimeters, and we're also told that it's cylindrical, so basically we're looking at a cylinder from the side, and the cylinder's radius is 28 centimeters, as I've tried to indicate on the figure. Furthermore, imagine that we're told that the system has constant uniform gas pressure, 500 kilopascals inside the piston. Now that is a unique characteristic to this problem. Generally speaking, in a piston you won't be guaranteed that the pressure will remain constant. You might expect it to change as a result of compression or expansion. Right now we're just going to consider a constant pressure case. Likewise, let's say that we're told the heat transfer value of Q equals minus 38 kilojoules, where if you recall from your lecture notes, the negative sign just tells you that heat is leaving our system and going out into the environment. Alright, let's do conservation of energy to solve for the change in internal energy of the gas. Well, as always, conservation of energy is that the change in total energy is Q minus W. Now, in this case, we can't set Q and W equal to 0 for obvious reasons. We have both heat transfer and work. We can actually set the kinetic and potential energy changes to be 0, though. In the case of the kinetic energy, the idea is that we moved the piston slowly enough that it didn't introduce large bulk flows into our system. Likewise, even if things moved around a little bit, it would be similar to turning off a ceiling fan and then watching what happens to the air in the room. It's not as though the air keeps circulating for an hour after you turn off the fan. Wait just a little while and that kinetic energy will be dissipated into internal energy. As for the potential energy, well, we can accept that there's probably not a big difference in potential energy as you compress the piston. If this thing were oriented vertically, that would be a different story. We would be pushing gas up or down. In this case, everything is horizontal. There shouldn't be a big change in potential energy at all. Our conservation of energy, therefore, becomes delta U equals Q minus W. Well, we're solving for delta U. We're given Q, so the tough part is figuring out the work. Looking at your lecture notes, an appropriate form for the work for a piston problem is the volume integral of the pressure. Now in this case, this is not a bad integral because we assume that the gas pressure was always constant, so we can actually pull it out of the integral and just get the integral of dV, which even on a bad day you can do. It's just the difference between V2 and V1. For a cylinder, the volume is pi r squared times L, where pi r squared is just the circular cross-section and L is the length of the cylinder. Well, we'll have to be careful. Pi r squared doesn't change, but the length of the cylinder does change effectively as you compress the piston. So if we move this up, we can put in subscripts on L to reflect that, substituting in that expression for the volume. So the work is now the pressure times the difference in volumes written in terms of R and L. We can pull out the pi r squared. Now we just need to figure out what L2 and L1 are. The easiest way to do this is actually to draw out the initial length and the final length of the piston. So L1 would correspond to this length over here, the full length before we started compressing the piston. L2 is the shorter length here after it has been compressed by 45 centimeters. Looking at this, it's clear that L2 minus L1 has to be a negative number because L2 is a positive value, but it's smaller than L1. L2 minus L1 has to be negative, and their difference is minus 45 centimeters. We can plug that into the work expression with all of the other values that we have in this problem. And we'll get out a value in kilojoules if we keep the pressure in kilopascals. That's fine. You want to make sure that you're relating things to SI units cleanly. So the work in this case is minus 55.4 kilojoules. That form of the work that we use to calculate this value is consistent with the sign convention in this class. So a negative work, if you'll recall from your lecture notes, tells you that energy has been added to our system, at least through work. Now we have to combine this work value with the heat transfer to see if the internal energy went up or down. It's not immediately obvious until you compare the two numbers. So going back to our expression of delta U equals Q minus W, we plug in Q is minus 38 kilojoules. We found that the work is minus 55.4, but the conservation of energy has a minus sign in front of that, so the change in internal energy of our system is 17.4 kilojoules. That tells us that indeed energy was added to our system despite the fact that heat transfer took some energy out. It didn't take as much energy out as the work put in. So the net gain in internal energy was 17.4 kilojoules. This problem would have been considerably tougher if the pressure hadn't been constant all that time. Consider that a preview of coming attractions.